All right, back to integration, back to finding antiderivatives. We've got a long way to go. We need some more techniques. So we've spent a little time applying what we've learned, looking at areas and volumes, and now we want to return to the discussion of finding an antiderivative, evaluating an indefinite integral. And of course, definite integrals, because those using the fundamental theorem of calculus part 1, we need the antiderivative. We've previously discussed the substitution method, which essentially undoes the chain rule. We're now going to look at something known as integration by parts, which really comes from the product rule and sort of undoes the product rule in a sense. If you remember the product rule from Calc 1, from first semester calculus, right? We have a derivative of a product of two differentiable functions. So what is that going to be? Hope you remember, you take the derivative of one function and multiply it times the other, and vice versa. So I hope you remember that, right? So the derivative of g times f plus the derivative of f times g, that's going to be the product rule, right? But since I know the derivative of this stuff in here, right, f times g is equal to this, then I know that this stuff here is the antiderivative of what's over here. Plus a constant, because you do plus c, right? But so this is just straight from what we know about the antiderivative, right? The antiderivative, since the derivative of this product is all this, then the antiderivative of all this is this product. Now I'm going to take a look at this integral over here. It's the sum of two things. I can split that up into two integrals. By the property of integrals, I can split this up into two, right? The linearity properties. Okay. And what I want to do now is I want to solve for this particular integral. I'm going to solve for this one. So in other words, I'm going to subtract this integral from both sides. And let me swap sides. In other words, I'll have the integral of f of x g of prime of x dx, solving for this one, is equal to this minus that one. So it's equal to the product f of x times g of x minus the integral f prime of x g of x dx. And so this really here is integration by parts. I'm going to put it in a slightly different form here in a minute. You say, well, how does this work? Well, what we're going to be dealing with is an integral of this form over here. So it's going to be a product, right? How do we deal with a product, an integration of a product of two functions? Well, if we can find that, a situation where we evaluate this, but then we have this integral to evaluate here. Well, look at this, g prime, and then here's g. So first of all, one function, I have to know its antiderivative. Okay, I know I have to know the antiderivative of that function, has to be known. If I don't know it, I can't use this method. And then the other function, certainly just taking its derivative here over here. But the idea is hopefully we choose in a way that this function here, when I take its derivative, this integral gets simpler. In other words, think of functions whose derivatives get simpler in a sense. The idea is I've got an integral over here to do, which is hard to do, difficult to do, don't know what it is, but I can do it in such a way, or I can use this to get an integral over here that's easier to do. If that's the case, if I can do this integral, I'm done, right? If I can find this antiderivative, then I've got this antiderivative. And so this is the so-called integration by parts, and you can kind of see we've got parts that we've broken this up into that we're going to be tackling. Now let me do a little substitution here. I'm going to let u be the function f of x. Now that u is not, this is not like substitute. I mean, we are doing a substitution here, essentially, but it's not the substitution method. So we've got a u here. I'm also going to have a v to be the other function, g of x. Okay. then the derivative of u with respect to x is f prime of x. So du is f prime of x dx. So that's kind of like substitution. In the same way, dv is g prime of x dx. And all I'm going to do then is replace what I have up here in terms of u's and v's. So I've got the integral f of x, which is u. G prime of x dx, g prime of x dx is dv, equals f of x, which is u, g of x, which is v, minus f prime of x dx, right, which is du, times g of x, which is v. So this is integral v du. And this is the way we usually write integration by parts. Integration by parts, I may abbreviate integration I by b parts p, IBP, integration by parts. Integration by parts, integral of u dv is equal to uv minus integral v du. So you will have to know this form. You might want to practice. It's a little confusing because you got a u dv and a v du, which goes with which. I'm going to talk about how to choose the u and the v here. How do we go about doing that? And notice it's real important these differentials play an important role. So if you don't like writing your dx's or your du's or your dv's in this case, you're going to be lost. You've got to include those differentials. So du is f prime of x dx, right? So this is the integration by parts formula. Here's the general guidelines. We want to choose the dv so that it can be integrated, because I'm going to integrate the dv part to get my v over here. So you've got to be able to integrate it. You choose the u so that the du dx is a simpler function. Okay, so in general, when we're choosing the u, because the u I'm going to differentiate, it's going to become the du over here. There's an acronym, it is LIATE is the way you could say it, L-I-A-T-E. So it kind of sounds like a fancy coffee drink. I don't know, LIATE. Okay, so L-I-A-T-E. What's that stand for? L stands for log functions. I is inverse trig functions. A is algebraic. T is trig. E is exponential. This is the order you would choose. In other words, actually, if you see a log function, typically that's the best choice for you. Let u be the function involving the logarithm. If there's no logarithm, next, is there an inverse trig function? Inverse sine, inverse cosine, inverse tangent? Choose u to be that, interestingly enough. Not till the third choice becomes algebraic. What are algebraic functions? Like polynomials, x squared plus 3x and so on like that. Choose algebraic. Then come trig functions, sine, cosine, secant, cosecant, and those. And then lastly, exponential functions like e to the x. The reason we got these at the bottom, the idea is to choose u so it gets simpler. If you choose u to be e to the x, well, the derivative of e to the x is just e to the x. Or the derivative of 2 to the x is what? Natural log of 2 times 2 to the x. So it's not getting any simpler. It's staying the same. Trig functions, you take the derivative of sine, you get cosine. Take the derivative of cosine, you get negative sine. Derivative of tangent is secant squared. That doesn't seem to be getting simpler. So really, these are bad choices down here. But here, algebraic, they get simpler, right? X squared becomes 2x, or 2x just becomes 2. Inverse trig, they get simpler in the sense that the inverse tangent, for instance, its derivative is 1 divided by 1 plus x squared, right? So it gets simpler in terms of, not being transcendental anymore. It's just algebraic. And log functions like the natural log of x, its derivative is 1 over x, so it too gets simpler. So those are the main choices. Let's take a look at some examples now. So we'll start with this simple example. We got x times cosine of x. So which function do we choose to be u, x or cosine of x? X is algebraic, cosine of x is trigonometric. Well, algebraic before trigonometric, right? So I'm going to choose u to be x, and that leaves dv to be everything else, cosine x dx. So you choose your u and you choose your dv. Well, once you choose your u, everything else is the dv. And then here, we're going to differentiate. Find the derivative, right? So what's the derivative of u with respect to x? It's just 1, right? Derivative. So du is equal to dx, we would say. Right? Du is equal to dx. Sorry. Over here, we're going to integrate. So I've got the integral of dv is equal to the integral of cosine x dx. Well, the integral of dv, that's just v. The integral of cosine x is what? What's the antiderivative of cosine x? Answer, sine of x. Now, yes, we have a plus c. Hold off on the plus c for now. We'll put it in when we get everything done. Okay, we'll add our plus c when everything is done. All right, so now we have our integral u dv is uv minus integral v du. So here we've got everything covered, right? Let's write this out. I've got the integral of u dv. So u again was x, and the dv was cosine x dx, right? So that's everything from our integral covered. And this is by the rule uv minus integral v du. That's the integration by parts formula. So what do I got for u? What's u? Well, u is x. What do I got for v? Well, v we had to compute is sine of x minus integral v, which is sine of x, but don't forget your du. What's your du? du is dx. So everything gets replaced with its appropriate expression. And now, what do we have? The integral of sine of x. Can we do that? What's the antiderivative of sine of x? Is it negative or positive cosine of x? It's negative cosine of x, so you got to be careful, right? And now, after I've evaluated all my integrals on this side, I can go ahead and do my plus c now. So clean it up. The answer is x sine of x minus plus cosine of x plus c. That's the integral, again, of x times cosine of x. All right, there's our answer. And you can check this by differentiating, right? Notice I can check by taking the derivative with respect to x of x sine of x plus cosine of x plus c, but again, a derivative of any constant is 0. So what do I have here? I've got product rule, right? Interestingly enough, we said that this integration by parts formula is undoing product rule, so it's no surprise that we got product rule when we check. So remember, you take the derivative of the first function, derivative of x is 1 times sine of x plus x times the derivative of sine of x, which is cosine of x, plus the derivative of cosine of x, which is negative sine of x. And you see what happens? I have 1 sine of x minus a sine of x. That's 0, and you're just left with what? X times cosine of x, right? And that's exactly what we need it to be, right? To get back to x integral, antiderivative of x cosine of x is this stuff. And I've proven it by taking the derivative. But this is the integration by parts technique. Okay. So let's look at some examples, shall we? Some more examples, I guess. Let's keep our formula up here at the top, and we'll take a look at this one. Okay. Again, what am I going to choose my u to be? I've got x and an e to the 2x. So I've got an algebraic and an exponential. Look at our list of choices here, right? In order, we choose log first, exponential last. So I'm not going to choose the e to the 2x to be u. X is algebraic. X is algebraic. So I'm going to choose u to be x. That means the dv is e to the 2x dx. Okay. So here I take my derivative, du, and I get just dx. Here I integrate. The integral is v. Here it's what? What's the antiderivative of e to the 2x? Now be careful. There's a small substitution in there, right? There's a small substitution. If you let u be 2x, you got e to the u, but your du would be 2 dx. So you need a 1/2 factor, right? So this is 1/2 e to the 2x plus c. So that right there is by substitution. So substitution is not going to go away. It will pop up in all sorts of settings. You need to be very well versed in that. Make sure you understand substitution method. So again, choose u to be 2x to be able to get this. So be careful, the antiderivative of e to the 2x is not e to the 2x. Just take the derivative of e to the 2x, and you know you've got a chain rule there. Okay, so you need this 1/2 factor in front of it. Okay, and I did a plus c. I don't really need a plus c, sorry. We'll put the plus c at the end. Okay, so now we're ready to put everything into position. The integral of u dv, right, this is u dv, is u, which is x, so that's the u, v, which we just found is 1/2 e to the 2x, that's v, minus the integral of v du. V is 1/2 e to the 2x, and then the du is just dx. So cleaning this up a little bit, I've got 1/2 x e to the 2x minus, let's pull that 1/2 out, the integral of e to the 2x. Well, integral of e to the 2x sounds familiar. We just did it up here, right? What's this? This right here is going to be, again, 1/2 e to the 2x. But I got a half times a half. That's a fourth, right? So it's 1/2 x e to the 2x minus 1/4 e to the 2x plus c. There's my plus c I put on at the end. There's the antiderivative for x times e to the 2x. Let's try one more. X to the 6 times natural log of x. What am I going to choose my u to be this time? I've got x to the 6, which is algebraic, natural log of x, which is logarithmic, Liate, right? Log functions before algebraic. So I'm actually going to choose my u to be, in this case, natural log of x. And that leaves my dv to be x to the 6th dx. Now be careful, again, we differentiate here. What's the derivative of u with respect to x? What's the derivative of natural log of x? That's 1 over x. So I get 1 over x dx. Here I integrate, right? So what's the antiderivative of x to the 6th? It's power rule, right? It's 1/7 x to the 7th. Right? Take the derivative of v and you get x to the 6th dx. So the integral, remember, of u dv is uv minus v du. So u is natural log of x, v is 1/7 x to the 7th, minus integral v, which is 1/7 x to the 7th, and then du, which is 1 over x dx. Okay, now be careful, right? Obviously here we've got 1/7 x to the 7th times the natural log of x. I'll just write it that way. Minus, now should we find antiderivative of this and antiderivative of this or something? No, you simplify this. You can't do that. It's a product. X to the 7th divided by x is what? X to the 6th. This 1/7 comes out in front. Got the integral of x to the 6th dx. What's the antiderivative of x to the 6th? Well, we just did that one again. That's 1/7 x to the 7th. 1/7 times 1/7 is 1/49th. And so here is my final antiderivative, minus 1/49th x to the 7th, plus, don't forget your plus c at the end. And again, you can see each time we're getting this, we're getting products of functions, right, in our antiderivative, as we should, because this essentially is undoing, if you will, the product rule. Well, it's using the product rule from derivatives to help us set up this integration by parts formula. Okay. All right, we'll stop here. The next one you might want to take a look at. We'll look at this one the beginning of the next video. What about that? You say there's no product there, it's just natural log of x. Oh, integral natural log of x, I know that, that's 1 over x, right? Is that right? I want you to think about that, and we'll talk about it in the next video.